So you know how to write code, right? But what does it really take to build something that doesn't just work today, but lasts for years? We're going to go way beyond syntax and loops and talk about the huge mindset shift from just being a coder to becoming a true software engineer. It's about thinking like an architect, not just someone laying bricks. Let's start with a really basic question. We're all just writing instructions for a computer. It should be straightforward. So why is it that so many software projects just spiral out of control? They go way over budget, they miss every deadline, or sometimes they just fail completely. What makes this so incredibly hard? Yeah, let's put that question right up front. Because if you can understand why software is so difficult to get right, you're taking the first step to mastering the very discipline that was invented to solve that problem, software engineering. And when things go wrong, well, the results can be weird. Check out this real-life story from 1992. A software bug, probably a classic two-digit year problem, sent an invitation for kindergarten to a 104-year-old woman. Now, that's kind of funny, sure, but it perfectly shows how software bugs don't just stay inside the computer. They leak out and have very strange, very real impacts on the world. So all this difficulty really comes down to three main areas. First, you've got the problem domain. That's just trying to understand the messy, complicated, real-world issue you're trying to solve. Then you have the solution domain. That's the technical challenge of the code itself. And finally, there's managing the development process, the people, the communication, the deadlines. Any one of these can sink a project. Okay, so this brings us to what is probably the single most important idea we're going to talk about. To really think like an engineer, you have to get past the biggest misconception people have about what we do. And here it is. Seriously, if you only remember one thing from this, make it this slide. Software engineering is not the same as coding. Coding is a part of it, an absolutely crucial part, but it isn't the whole story. Saying it is, well, it's like saying architecture is just about laying bricks. The real engineering work happens long before the first line of code is ever typed. So if it's not just coding, what is it? At its heart, software engineering is a problem-solving activity. It's a formal discipline. It's about deeply understanding a problem, breaking it down into manageable pieces, and then building a thought-out, structured solution. And this whole problem-solving process really boils down to two key actions. You got to remember these two words. First comes analysis. That's where you take the big, messy problem and break it apart to understand every little piece. Then comes synthesis. That's the magic of putting all those pieces back together into a large, coherent, working system. Okay, so if we're up against all this complexity, how in the world do we manage it all? Well, we do it by adopting an engineering discipline. So let's look at the basic building blocks that engineers use to tackle these huge challenges without getting totally lost. This right here, this is the goal. This is what it's all about. Look, anyone can build something if they have unlimited time and unlimited money. The real trick, the engineering challenge, is to produce a high-quality system on time, on budget, and, here's the kicker, while dealing with the one thing you can always count on, constant change. To make this happen, we use a few key concepts. First up is a technique. The best way to think about this is like a single recipe in a cookbook. It's a formal step-by-step procedure for doing one specific thing to get a predictable result. Okay, so if a technique is just one recipe, then a methodology is the entire cookbook. It's a whole collection of techniques all brought together under a single guiding philosophy. Think of something like Agile or Waterfall. Those are different cookbooks, different methodologies for building software. And of course, you can't cook without your tools, right? You need your pots, your pans, your stove. In our world, a tool is anything from a compiler to a debugger to a version control system. You'll often hear these called CASE tools. That stands for Computer-Aided Software Engineering, and they're just the instruments we use to get the job done. All right, enough with the abstract ideas. Let's get into one of the most powerful and practical tools in an engineer's toolbox: modeling. This is all about drawing a blueprint before you start building the house. And when it comes to software blueprints, there is one language that everybody in the industry uses. It's the standard, and it's called UML, which stands for Unified Modeling Language. Just like a building architect has a standard way to draw plans, we use UML to draw our systems so everyone is on the same page. So check this out. This is a classic use case diagram. What's so great about it is that it forces you to think from the user's point of view. See those little stick figures? We call them actors. They could be a customer, an admin, whatever. And the ovals? Those are the use cases, the actual things the actors can do. This blueprint isn't about code at all. It just answers the simple question, what can people do with this system? Okay, so if the use case diagram showed us what the system does from the outside, this one, the object model, shows us what the system is made of on the inside. This is the blueprint for the static structure. Each of these boxes represents a piece of the system, like a client or an order. It shows all the parts and how they're connected to each other before anything actually starts happening. And that brings us to the dynamic model, which you're seeing here as a sequence diagram. If the last model was the list of parts, think of this as the instruction manual showing how those parts work together over time. It shows the how. You read it from top to bottom, and it visualizes the messages being passed back and forth between objects to get a single job done. It's basically a comic strip for one function. All right, I know that was a lot, so let's boil it all down to the absolute essentials. If you're studying this stuff, this next slide is your cheat sheet. This is the one you really want to commit to memory. Okay, here are the 4 big takeaways. Number 1, software engineering isn't coding, it's problem solving, which means analysis and synthesis. Number 2, we use a structured approach built on techniques, methodologies, and tools. Number 3, the goal is always to deliver a quality product on time and on budget, even when things are constantly changing. And finally, number 4, UML is the critical language we use to visualize and communicate our design. So I'll just leave you with this one thought. The next time you start a project, are you going to approach it as a coder or as an engineer? Are you going to jump right into writing code, or are you going to step back first, analyze the problem, and actually design a solution? Because that choice, that little shift in mindset, that changes everything.